We begin lecture 30 with a brief review of what we had talked in the last class, namely the sixth order scheme of Lele that was obtained by Taylor series analysis. However, we also pointed out that there must be some basis for choosing compact scheme. One way of doing it was a optimization of the scheme by looking at the truncation error, as we talked about in the last class about Haras and Tassan's method of looking at it in the K space instead of worrying about the physical plane matching term by term, and in the process we can develop very accurate schemes, but whose order could be very less. That naturally brings us to this discussion on the distinction between order of approximation versus resolution of the scheme, and we will surely highlight that what is more important is the resolution of the scheme rather than formal order of approximation. And in the process, we also figure out why compact schemes are so accurate as compared to other methods, because of its global nature, and that global nature can be found out very clearly by an analysis that we have developed, the spectral analysis tool. We can figure out that this implicit method, when written as an equivalent explicit scheme, that is equivalent to 20th or higher order accurate scheme. So, this is one of the plus points of compact schemes as a global approximation, and we have further developed the spectral analysis tool by finding out the resolution at any node for a non-periodic problem in terms of a projection operator. That is what we are going to talk about. And once we do that, taking the derivative is equivalent to converting the k, the wave number, into an equivalent k, which we have called as k eq, which will have now a real and imaginary part. The real part actually represents the phase, while the imaginary part represents dissipation or anti-diffusion. This is rather important, because we just will show using one of the older scheme due to Adams that near the boundary this scheme actually shows very large dissipation near the outflow and instability near the inflow. Then we will also talk about Carpenter's scheme of fourth order accuracy, and we noticed that this method also has a problem with the boundary closure. So, this is essentially due to the asymmetry of all compact schemes. So, we have to be extremely careful in how we get this boundary stencil in the compact scheme, and this is this has led to upwind compact scheme, which we will be talking about, but we will in the meanwhile talk about evaluating second derivative as a sequence of two first derivative operation, and with this we will conclude lecture 30. We were looking at high accuracy methods of computing, and in that context we were talking about compact schemes. Compact schemes, typical example is given here in equation 9, where the derivatives determined by this primed quantities on the left hand side are related to the function on the right hand side. You can see that these are implicit methods, because the derivatives that we are looking for, they are coupled in this equation, as opposed to explicit methods that we have done before. So, there are some constants alpha on the left hand side, a and b on the right hand side. H is the spacing between the nodes, and then what you can do is you can equate the coefficients of Taylor series on both sides, and when you equate the coefficients of u prime on the left hand side, of course, you note it gives you 1 plus 2 alpha, and on the right hand side it is a plus b. The next coefficient was the third derivative terms coefficients, and on the left hand side you get it alpha, and on the right hand side you get a plus 4b by 6, and so on and so forth. So what happens is these three coefficients are found out by solving, let's say, these three equations 10 to 12, and that's how you get three values of this constants, and this is what we usually would get. These are unique set of values of constants for this particular case, and since you have satisfied this Taylor series expansion 9 up to fifth derivative, so next drop term is the seventh derivative. That's why we called it a sixth order scheme, and I emphasize the fact that you would always be satisfying equation 10, and that is the coefficient of u prime, because that's what you are trying to find out. So since you are looking for u prime, there is no way you can forget equation 10. Satisfaction of 10 is a must, and this is what we call as the consistency condition, and this was a unique scheme given here, alpha a and b. And we talked about that the leading truncation error is the seventh derivative term. That's why it is called sixth order scheme. We talked about Lele's effort in trying to develop a fourth order scheme. Fourth order scheme means you would have satisfied 10 and 11 and omitted 12, and that would give you two equations and three unknowns. So you get one parameter family scheme. Let's take alpha be that parameter, then you can get a and b in terms of alpha. Okay, so we did talk about this, and we said that look, this coefficients that we are seeing, they are all real numbers. However, they are to be a sort of a continuum, in the sense they are not like Dirac functions that only at the chosen value you have defined and everywhere the error is degraded. That's the question that we posed here, that they are not whether they are discontinuous function or continuous function, and we did come later and discuss furthermore, saying that they are indeed continuous functions, and that opens up possibility of obtaining optimized schemes. You can optimize it. That's what Haras and Tassan did. They did optimize a scheme for evaluating the first derivative by minimizing the error committed by this approach with respect to the spectral method, and they tried to look at the full range of k for the wave equation only, and that was somewhat different than what Lele tried to do earlier. He also tried his hand at optimization, but because there were three equations, three unknowns, so he looked at the departure at three values of k, and from there he obtained the values. Okay, and Lele observed, which is the core of this subject, that if you take a look at this optimized or non-optimized implicit schemes, they are far more accurate than their counterpart in the explicit schemes, and this could be quite significant. That, for example, a fourth order scheme that Lele obtained was outperforming a 10th order explicit scheme. So basically that made us observe that we really should not be bothered too much about looking at the truncation error. Instead, we should try to find out in the k space what is happening to error. That is the whole rule of this game. So basically we define what we call as the resolution. So resolution is, of course, what we are after. We are not worried too much about order of approximation, and resolution means that how well you are resolving all length scale in the problem. Okay. You may have noticed that we have already talked about the Nyquist criteria, the chosen grade. That is one criteria, but the resolution is not the Nyquist criteria. It is something lower than that, and that's what we need to figure out. And we basically would do that by looking at spectral analysis in the K space, and that's what we did subsequently. This is where you begin by expressing the unknown, let's say at the jth node, in terms of its Fourier Laplace transform. Please understand that this is integral, this is not a series, so this implies that you are able to take care of non-periodic problem. You are not necessarily solving a periodic problem. And if you recall that in this general framework, what we are doing, we are looking at a linear algebraic equation where the derivatives, let's say the first derivative is obtained by solving this linear algebraic equation. Okay, most of the time you would note that this A and B matrices are going to be constant valued matrices. So they do not depend on at what level of computation stage you are in. So you can do that. So what you can do is you can write it down instead of like this. U prime should be equal to Cu, where C is A inverse B. But please pay attention that in your actual computation you would never do this A inverse operation. What you just now notice that A matrix, as you can see from this equation on 9, would be the tridiagonal matrix, right? Even then, you would not be doing A inverse B. That is just for the sake of analysis, we are writing A inverse. In the actual case, you will always solving this equation because this will involve. So this is a tridiagonal matrix here. This could be at the most a pentagonal matrix. What you would notice that when you write down like this, U prime equal to A inverse B into U, what will be the bandwidth of the matrix? This is interesting because you see here you are solving the equation. Of course, on the right hand side you don't have to worry about whether it is pentadiagonal or heptadiagonal because your function values will be given. So you will be making up this product and it will be just a vector, right? So this will be a vector that you would be computing, and then you will be solving a tridiagonal matrix equation. That's the whole approach that you will be taking. So if I know the dimension, the rank of this matrix is n, then we do 5n to 7n calculations, right, in solving this equation. And if you do A inverse B, what do you think the bandwidth C matrix would be? Well, if you go ahead and perform that, you would be surprised to see that C matrix will have non-zero entries about the diagonal, which spans about 10, 11 points on either side. What does that mean? It means that C matrix is something like a banded matrix with 22 non-zero elements. So that would be something like your 22nd order or 23rd order equivalent explicit scheme, right? We did discuss it in the last class also. That say, for example, a second order scheme we require 3 points, the middle point and the neighbors, right? The fourth order we need 5 points. So if I have say 22 points, the bandwidth of C matrix is 22, then I am actually equivalently writing out about, let's say, a 23rd order scheme. So this is the clinching issue of compact scheme, that although you are solving a tridiagonal system, you are developing an equivalent explicit scheme which is of the order of 20 plus. That is a significant advantage that you should have. And this is the prime mover for this whole activity. Now you also notice that if we are looking at explicit scheme, what is A? A is going to be an identity matrix because we are explicitly finding the derivative at one point in terms of the function values. So A will be just simply nothing but an identity matrix. So that's what we said. So basically what we are trying to do, we are trying to develop a framework where we can analyze a scheme. It's not necessarily has to be finite difference, finite volume or finite element. All you need to do is come to this level. A and B. Time permitting, I will just tell you how to construct finite element methods in this whatever little time we would have, and there we would note that this A and B matrix once again are going to be some constant valued matrices. So this framework that we are setting up is going to be rather generic, and you could use it for any discretization scheme that you would like to. Okay. So one thing that we did talk about is this bandwidth, which we are now familiar. That C is not necessarily bandwidth by the bandwidth of A and B. So this is a major issue that I emphasize again, that compact scheme appears local in nature, because if you are looking at jth point on the left hand side, you have at the most j plus 1 and j minus 1. So that makes it local, right? However, because of this A inverse B operation makes the C matrix bandwidth rather large, so that makes it basically a global approximation, and this is what we call as the global near spectral approximation. It is so good now, let me tell you, the compact schemes are so much more handy and accurate that so-called spectral element method, an offshoot of finite element method that is often used by many people, although they call it a spectral element, but they do use Lagrange interpolation functions of the order of 3, 4, or 5 at the most. There the accuracy is that much, whereas this provides you with a much greater accuracy and much more flexibility in solving problems. Okay. So what we are essentially saying in the last bullet is that if we are looking at any generic compact scheme, we can construct an equivalent explicit scheme, right? That is the connection between an implicit and an explicit scheme. Okay. So for example, say you are trying to obtain the first derivative, as we have seen here. First derivative is equivalent to multiplying the Fourier loss amplitude u of k by simply I k. Okay. And then let's say if we are trying to evaluate, I think there is a mistake, this thing should be UL prime. So what we are trying to do is we are trying to find out the derivative at the Lth node. So if I want to write this, what I should be writing here, ik u of k e to the power ik xl dk. Right? This is the spectral representation of this. However, what we are doing here, we are writing it like this. So what we are doing, in a sense, a priori we do not know how many of those functions are involved. So we would assume that B is full. So that means we are taking the contribution from each and every node. So what happens is we could project this, let's say I could project it at any other point, say I could write it like e to the power I k, and then e to the power I k, I will write xl minus xk. So this quantity, if I call this as some projection of the jth node onto the Lth node, so that's what we have written here in equation 17. So although my derivative is on the left hand side is relates to the Lth point, whereas I am evaluating the phase at the jth nodes, all the jth nodes, and then what will happen is if I just look at one particular point xj, then I need to multiply by this projection operator. That's what we have written here. Okay. So you can see with a uniformly spaced point, that will be simply nothing but ikh times L minus j, and that basically is further split into a real part and the imaginary part. Real I call it as RLJ, and plus iota into ILJ. Now, so if I like to write the derivative at say jth node, I can write it here because on the right hand side we have a contribution coming from all the other nodes. Nonetheless, what we try to do, we try to write an equivalent form where the phase is essentially written at the jth node. You have to understand that whenever we do this derivative operation, these are local operation, means I am trying to find out derivative at the lth node. My phase is dictated upon by this quantity evaluated at the lth point itself, whereas numerically what we try to do, numerically we try to add up all the points contribution in the domain, right. That is what this right hand side implies, that I am not, if I am trying to find out the jth point, this is not necessarily at the jth point, but this is from U1 to UN. All the points are coming into picture, and that's what we are trying to state here, that I have a sort of a global operation in numerical sense, but if we were to find out what is happening in the corresponding theoretical spectral explanation mode, then I should look at this, because now what has happened here, this is like uj prime on the left hand side, and this is my C matrix, and this is my let me write this. So what is this C matrix is? Suppose I want to find out uj prime, what I would do, I would take the jth row and multiply by the whole column, right. So that's precisely what we have done here. That's what you are seeing here. I have taken the jth row and I have multiplied. I have done that phase shift business. I project each and every point to the jth point. U1 has been projected to uj by having this, and so on and so forth. So that's why this quantities within brace tells you how the projection has been taken with the help of the C matrix. C matrix is also again a constant coefficient matrix, so you do not have to worry about anything. These are easily obtainable. Okay. So having obtained this, now what happens if this is my spectral representation? What we have done in a computational sense, we would have done it like this. Instead of ik, we would have obtained some ik equivalent. We know now how to calculate ik equivalent. I will show you here also. And then I would have multiplied by u of k. And then ideally I would have liked to be getting it at the lth node itself, but I am doing it like ik h. If I am doing it L minus G. So this is what we are getting. This is what we want, right? So what happens is, if I look at this, so every uj or ul has been projected to the jth point, and that projection operation is given here, right. This is what we are getting. This is the projection, and then of course you brought the phase back to the jth node. That's what we are looking at. So this is essentially then the quantity within that brace is nothing but ik equivalent, right. That is your ik equivalent. So ik equivalent is nothing but your CJL into PLJ, and that you have to sum over all the nodes L running from 1 to n. So that's what I said, that you could write your ik equivalent at the jth node in terms of the jth row of the C matrix multiplying by that projection operator PLJ. Okay. So this is the story, that you can now calculate k equivalent And remember, this is something that we have achieved now. We have been able to find out this k equivalent at all the nodes simultaneously, right. It's not a local analysis, it's now a global analysis, because all the nodes L equal to 1 to n are involved in evaluating the k equivalent at the jth node. Okay. So this is something that we did, and tell you what, this was not very old story. This we did over here itself only a few years ago. One of our BTech student, Gaurav Ganeri, he joined me in doing this, and before that this did not exist. So in a sense, I think we did develop a spectral matrix analysis, stability analysis over the whole domain. This is important because local analysis is good, but in the long run what you need to know is how you are solving the problem in the full domain, and you would know how each alteration at one point can affect the other points. So this is what we need to do. Now the second point that you need to notice, that this k equivalent that you are obtaining is essentially a complex number, right, with the real part. The real part will be giving you what? So here also I would be writing here some k equivalent. Okay. So if I now write that k equivalent to consist of a real part then what happens is, of course, if I am looking at ik equivalent, so this part is going to give me the phase part, right. That you can easily see, the real part actually contributes to the phase. However, this, what does the imaginary part do? Look at the iota sitting outside and there is one inside. So this will give us something like e to the power minus k imaginary into x. So whenever you would estimate this k equivalent, the real part would tell you how well the phase has been represented, while the imaginary part will tell you if you have added numerical dissipation. See, that is why we have been discussing so far about central schemes. We do not want to needlessly bring in numerical dissipation, because chances are that will cause the solution to attenuate unphysically. So to avoid that, what we are doing, we are looking at central scheme. But suppose we have also seen that even though we are dealing with the central scheme, that near the boundary we still have to close the system. We said that we will have to bring in near boundary stencil, which will only get information from inside the domain. So on the left hand side it will come from inside, that will go from right to left, and on the other side you would get it from inside towards outside. So we have talked about it. So those boundary closure, the closing the boundary points, would still bring us to one sided schemes. And as you now have seen, that if I have this A and B matrix which are not perfectly central, because the first row and the last row will have to change because of lack of information from outside the domain, we will have to keep one sided analysis. And then what happens is you will get a C matrix which will not be symmetric, which will be non-symmetric, and that in turn will give you a k equivalent which will have an imaginary part. Why? Because you have seen that k equivalent comes from the C matrix here, right? C matrix. If the C matrix is non-symmetric, then you can be rest assured that this will be non-symmetric, and you will have a imaginary part, and that can add to numerical dissipation. And if you are not careful, which happened to most of the people before we stepped in, we found that many of the schemes those are being popular and used, that instead of numerical dissipation, they are having just the opposite effect. They were actually making the flow unstable. The problem, the signals were propagating with the amplitude growing. That means k imaginary, instead of being negative were actually becoming positive. I'll explain again. Please do understand that, well, let me explain with the help of an example to understand this role of real and imaginary part. This would be useful. Suppose, let's take our simple example here. If I am trying to solve this equation, now if I add numerical dissipation, then what do I do? I would add some, I don't know, let me call this nu. See, if nu is going to be a positive quantity, then of course you are dissipating the solution, right? This is like adding a physical dissipation. So if I have a method where instead of solving this equation, I have an equivalent equation of this kind, what am I doing? I am actually adding a dissipative term only when nu is positive. If nu is negative, the way we are doing here, then we will be actually, instead of adding dissipation, we will be pumping in energy to the system, right. So if so this is what I would call a dissipative method. So let me put this instead, if I get this like this, a strictly negative quantity, then what do I get? This will be not dissipative, just the opposite of that. So people have called it as anti-diffusive method. So we are adding anti-diffusion. Okay. So if I now go back and look at the methodologies we are talking about here, yeah, look at equation 22. Now if I have K equivalent like this, then what am I getting? K equivalent U of K, then e to the power I K equivalent x of j dk. This is what? This is, let's say we are finding out del u del x at xj location. That is what we are finding out. Okay. Now say K equivalent has a real and imaginary part itself. Well, let me write it. This part I am just leaving it as it is. Now what happens? This I could write it as I K real U of K e to the power I K equivalent xj dk, and I will get minus K imaginary U of K okay. So now you see this equation, if you look at this equation here, what we are getting here is this del u del t plus this is this part. So this is this part, that is C times this, and this is additionally that has been brought in here. So I could take it on the other side, then you can see the role of K imaginary. So now you see there is no iota here, like here there is I. So this is like your a second derivative brought in there. Now you can see what we are talking about. If K imaginary is negative, then what will happen here? If it is positive, it will work as a diffusive term, but if it is negative, it will work as an anti-diffusive term. So, this is something you have to realize, that how important it is for one to obtain this K equivalent, and then you would like to probably plot it in a non-dimensional form by scaling it with respect to the corresponding theoretical estimate. So, that is why we will be plotting K equivalent by K, and of course, by now you are comfortable with the idea that instead of plotting it across as a function of K, we will be plotting it as a function of Kh. Okay. That will make your job easier, because all the time we will be plotting between 0 and pi. That is the universal limit, right, set by Nyquist limit. So, that is what I just restate here. The ratio reflects the efficiency of a method with respect to the best theoretical estimate that you can get through the spectral method. Okay. Now, I emphasized also this part, that if you would choose a symmetric stencil for the interior nodes, that would give rise to K equivalent, which will not have the imaginary part, and that would actually mean that you are developing a non-dissipative scheme. That is what the second bullet states. However, we have also seen that we are forced to take asymmetric stencil for the boundary and near boundary points, that would make the method either dissipative or non-dissipative near the boundaries, and this is an implicit threat of compact schemes. Okay. So, we have to be wary of it, and we have to guard against it. Okay. We will have to figure it out, and we have also seen that these are all matrix operations. So, even if I do something at say j equal to 1 or 2, its effect will percolate much more deep inside the domain. So, this is what it is. So, let us look at some of the things which people have been doing. This was taken from Nick Adams' thesis work. He suggested that use a interior stencil like this, and as you can see, this is on the right hand side we have a 5-point molecule like what we have already stated, and this you can do it only from 3 to n minus 2. So, you need to have closures at j equal to 1 and j equal to 2, and as we kept saying time and again, this will have to be one sided. So, at j equal to 1, it would be a admixture of u1 prime and u2 prime on the left hand side, and on the right hand side also it has to be one sided, right. So, that is what is done here. You can convince yourself, you must do it yourself, do a Taylor series expansion and check what is the sort of order of this scheme. Okay. You would be noticing that you are matching the first and third derivative. So, this is essentially a fourth derivative stencil, that fourth order stencil that you see in 23. Same about this also, for j equal to 2, you take a stencil. Well, this is somewhat slightly better. On the left hand side again you have a symmetry though, 1 4 1, and same thing about the right hand side also. You can see there is a anti-symmetry, that is what you require. 3 and 1 both have amplitude equal to 1. So, it is the point j equal to 1 that may give rise to some problem, whereas rest of the point you have a perfectly symmetric stencil on the left hand side that you see 1 3 1, and on the right hand side you again get what you want, the antisymmetric coefficients, right. J minus 2 is minus 1 and j plus 2 is plus 1, j minus 1 is minus 28 and j plus 1 is plus 28, all are divided by 12h. So, you can see that again we can do a Taylor series expansion, and you would probably note that these are 6th order accurate schemes. Okay. So, basically Adams started looking at these problems using a 6th order interior stencil and 4th order boundary stencil. What do? You have to do a similar thing at j equal to n minus 1 and j equal to n. j equal to n minus 1 would be nothing but a mirror image of 24. Okay. So, this will be u n, this will be u n minus 1 and this will be u n minus 2, whereas what will happen here? Please note this, that while on the left hand side the coefficients remain as they are, on the right hand side you are going to see an antisymmetry. So, you will write it here for 24. Okay. Instead of 3 we would be writing u n minus 2 and this will be u n, but in addition we must have a minus sign. You can convince yourself that this would be just the antisymmetric representation of the right hand side of 24. Okay. So, same thing holds for j equal to n, that would be a mirror image of j equal to 1, left hand side coefficients remain as they are. So, replace u n prime by u n prime and u 2 prime by u n minus 1 prime, and on the right hand side you will be writing, instead of minus 5 u 1 you will be writing plus 5 u n, then instead of writing 4 u 2 you will be writing minus 4 u n minus 1 and then minus u n minus 2. Okay. So, this is the way you have the full A and B matrix set up for you. Okay. And all the time whenever you need to calculate these derivatives which are given on the left hand side, you will be solving this equation by tridiagonal matrix algorithm, right. So, that is the practicality of this issue. Okay. I think that is what we explained just there, that we have near boundary point stencil which are 4th order accurate and the interior points are 6th order accurate, formal accuracy, and this is one of the scheme that was used by Adams. There is this group from NASA Langley, Carpenter and their group, they used this type of scheme and what I just now said, I just showing you here. So, what about this scheme 27? 27 is basically something like what Adams took actually for the interior, sorry, for 24. You see, Adams took this scheme which is a 4th order accurate scheme, but it is symmetric, that is what I mentioned. So, in the Carpenter scheme the interior nodes are actually this, the same equation that Adams did. This is for j equal to 2 to n minus 1. You can see they can be applied all the way up to 2 to n minus 1. You need to only close the system by having a scheme for j equal to 1 and j equal to n. Okay. So, these two are written here, these two are written here, and what I said about how to write out the antisymmetric scheme, 28 is just the antisymmetry of 26 on the right hand side, that you can see. Okay. To compare with this 4th order accurate compact scheme, Carpenter also looked at explicit 4th order schemes, and this is what is given here. And you see, when you go to explicit 4th order scheme, on the right hand side in 31 you can see you need j minus 2 to j plus 2. So, you can write it for 3 to n minus 2. So, even though you are doing explicit method, your work actually increases because you have to have 2 more additional closure schemes for j equal to 1 and j equal to 2. Okay. And they are also written like this, and I suppose this 29 and 30 they are also formally 4th order accurate. So, the whole idea in this exercise by Carpenter and his colleagues were to compare a 4th order explicit versus 4th order implicit scheme. I will show you the result. Now, I think maybe I should first show you the result, then we will come back here again. So, if I look at 4th order implicit scheme, what we have here is on this side we have plotted k equivalent by k, and on this side we have plotted kh, and you can see we have taken a domain from j equal to 1 to let us say 31, and we are showing half the number of points because it is perfectly symmetric. So, if you see only one half, you can imagine what is happening on the other half, because they will be coincident on the real part. So, the left hand side is the real part of k equivalent by k, and ideally you would want it to be equal to 1 to as large a range of kh as possible, right. That is what we want, because in a spectral method that remains 1 all the way up to kh equal to pi, and then it falls off at the Nyquist limits. So, we would like to do that, but in this compact schemes you would notice they do remain 1 to a pretty large extent, and then they start falling off, and this is what we call a filtering of the solution. You see, this is what you may have done. I do not know if any of you have taken this course on electrical engineering. They talk about filtering, low pass, high pass filter. Well, you may have system, you have seen how those filters work. So, you can tune the filter and selectively attenuate or amplify different frequency band. So, it is also the same way here. Instead of time domain, we are looking at in space, and instead of looking at frequency, we are looking at wave number. That is the only essential difference, but other ideas are exactly same. So, what you see that compact schemes or any discrete scheme has this attribute as we have plotted. We have seen that they have this attitude approach to make this k equivalent k go to 0 at pi. We have done it. We have done it if we have looked at CD2 and CD4 expansion in the previous part. This is what happens. However, you notice one very interesting thing about this. At j equal to 1, that is the inflow part of the domain. Look at this. It has a very exaggerated overshoot. What does it mean? That some of those intermediate wave numbers are weighted more than they would have been even for a spectral method. Whether this overemphasizing some k component is good or not, we will talk about it later. We will not appreciate it now, but we do agree that this is not physical. Physically, it should have been 1 and then it should have fallen to 0. And this departure overshoot is significantly more than this filtering attribute of any discrete scheme. Now, you also look at the imaginary part that is shown here, and we have plotted k equivalent by k imaginary part versus kh, and what you notice that j equal to 1 line actually goes off to a exceedingly high value, and this positive values, I think here we have taken a sign inbuilt into it. So, that is why all this positive values imply numerical instability. So, what it actually tells you, that in the process of spatial discretization itself, if you are not careful, instead of dissipating the solution, you actually are going to pump in energy, and that would be quite catastrophic. As you can see, you try to use this and try to solve even this equation, which is what you are going to do as your next assignment. I suppose you will get an hands-on experience in analyzing schemes and calibrating it with respect to a standard problem like this, and you would be able to see what this is doing. So, the first point is very badly behaved, as we can see here. This goes off to a value of k equivalent by k is 5 times. This is exceedingly high value, but the same thing happens with other nodes also, j equal to 2, 3 and so on and so forth. What you are seeing, that is what I mentioned a moment ago, that although you are making a mistake at j equal to 1, taking a wrongly directional stencil, that effect is percolating inside. You are seeing that its effect is felt at j equal to 2, 3 all the way, and only when you are substantially inside, then you see it is becoming what you want it to be. It is a symmetric scheme. So, you want the imaginary part to be 0, and that is what you are seeing only near the I would say j equal to maybe 13, 14, that is what you are getting. Even this value here, I think 5 or 6, they are unstable very clearly. You would also see that some of these things are very interesting, that it goes up and down. So, it shows you that instabilities are very selective in across a small range of k. So, you have to do that. So, this was what you see for the implicit scheme, and you can see that k equivalent by k here is equal to 1 all the way up to about 1, right. Well, it is even more than that, it is about 1.2 or something. Now, if you look at the corresponding explicit scheme, you can see what you are getting. The real path is on top, and you can see it falls off from a value of about 0.6 or so. So, although you are having both the methods at fourth order scheme, but explicit scheme allows you to maintain accuracy only up to 0.5, 0.6, whereas the implicit scheme allows you to go to twice the range, right. So, what does it mean? That if you are solving a problem, you should be able to do accurate calculation by taking half the number of points if you are adopting the implicit scheme as compared to the explicit scheme. So, if you have, let us say, a 3-dimensional problem, in each direction you get a benefit of this kind, a factor of 2 reduction. So, you are actually going to get by with maybe about half the number of points in each direction. That amounts to about 8 to 10 times benefit, right. So, in fact, I will come to some schemes which we have developed here itself. We get such benefit in each direction by a factor of 8 to 10, and you can understand that can translate into benefit of the order of 500 to 1000 times, and that is what we have been doing for last 10 years, using PC to compute problems which others use supercomputers to do. So, it is possible. So, we have exploited the benefit of implicit schemes. So, let us go back. So, this is what we talked about. Now, let us talk about another aspect. We have been talking about the first derivative, right. First derivative we are evaluating by solving this equation, or we are doing this u prime equal to C u. Now, suppose I want to evaluate the second derivative, then what I could do? I could equate the second derivative with the first derivative, right. This equation is that if I write this, so if I use this in here, I am going to get. So, basically we are doing it twice to get the second derivative. Now, what does it do? That is what we tried to understand, and we tried to do in the initial stages when we were at it. We tried to evaluate the second derivative by this equation 32, and what you are noticing here is that this has been done in 2 steps. First, you solve a u prime equal to b u, and then you again solve it again, a u double prime equal to b u prime. So, that is what is implied by equation 32 here. Okay. Then let us say, simplify the problem very much. We take that say some sort of a stencil which we had shown here, given here. There is a Adam scheme. So, we take n equal to 5. So, what we do is j equal to 1 we use this equation, j equal to 2 we use this, j equal to 3 we use 25, and for j equal to 4 we write out an expression which is similar to 24, and for j equal to 5 we write out an equivalent expression of 23. So, if we do this, then it is a nice C matrix is going to be nice 5 by 5 matrix, and then I suppose some of you may be familiar, you can use the symbolic manipulator, right. Maple or MATLAB toolbox also has it, Maxima is another one. So, you can use the symbolic manipulator and you can work out this C square matrix. See, all those schemes that I talked about, the Adam scheme, the interior stencil was 6th order accurate, the boundary closure schemes were 4th order accurate, and we used that, a combination of a 4th and 6th order, and we worked out the second derivative analytically using the symbolic manipulator. And you can see what this is. This is your CD2 expression. So, what happens to our obsession with order of accuracy. We used a 4th order and 6th order, and this is an exact operation. Symbolic manipulator comes back and tells you that in effect you are doing actually 2nd order accuracy. So, this is a clear evidence that worrying too much about the order of accuracy is not really something that we like to do. Okay. So, that is the last comment that I made there. Now, if I go back to that Adam scheme, and let me also tell you that the previous example also tells you that sometimes doing this analysis over unrealistically small number of points can give you such surprises. See, here this could be an attribute of taking only 5 points. Suppose I would have taken 8 points or 10 points, I would probably get something different, right. So, please do not overgeneralize. I think this comes as a warning for your exam question. You always saw a quadratic and you saw the product term is -1, all of you jumped the gun and said, okay, the product is 1, so 1 is more than 1, other is less than 1. That is not true. You have all forgotten that both of them could be equal to 1, and that is exactly what happens with leapfrog method. So, if you would have just done it, you would have, some of you have done it, you have seen it. So, please do not generalize, right. So, this is what we also seen, that we tried to see the sensitivity with n, and done this exercise with the Adam scheme with 20 points and 30 points, and when we saw there is absolutely no difference between the two sets of results, then go back and adopt one of them. So, we have if at all we have erred on the conservative side, all the results that you see are going to be with 30 points at least. So, if you take any more number of points, these are going to be not different. And this global analysis tells you how this k equivalent by k, the real part, varies with k age for different nodes. Once again, you can see this first node is always ill behaved, but this is somewhat much better than what Carpenter's method was. You saw the overshoot there reaching up to 3.5 and 4. Here it has gone up to less than 2.5, and we will talk about the role of j equal to 1 and j equal to n somewhat later, but let us first look at this result. So, they do not look too bad, you see. In the interior you have a 6th order scheme, and that is why you will see that k equivalent by k remains flat all the way up to 1.5, the value is 1. So, it shows you that out of the full Nyquist limit you are able to get almost half the range. Okay. I think this is instructive, because what we are going to do, the spectral methods are always used using uniform spacing. You cannot use spectral method using non-uniform spacing, whereas this compact scheme we can use it after mapping your governing equation to the transform plane, and in the transform plane you have equispaced nodes, there you can use this. So, this makes it somewhat of a utility that we will see as we go along. Okay.